Okay, let's start. Do you hear my voice?
Yes.
Okay, let's start. Frat, I need to talk to you about your homework. Okay, I will talk to you privately. Okay, so last time we started talking about the file systems, and we said that on a given disk there could be more than one file system. One of them could be a Unix file system, the other could be NTFS file system, and each file system has a different way of organizing their files. And after that, we said that let's look at how we organize the files on our disk. Okay, for example, in this case, I have one, two, three, four disk partitions, and each one may have a different file system, and it looks like the file system in the center, the disk partition in the center, uses the waiting for the bad network. It uses the inodes, so it's a Unix file system. And then we said that let's look at each let's look at the way each file system organize their files. That's what we were doing last time, and we said that okay, the first file system organization method is the contiguous layout. Okay, contiguous layout. With the contiguous layout, we said that this is very similar to a pure segmentation of memory structures. Okay, each file has its own consecutive blocks in the disk, so it has several advantages, such as organizing is so simple. All you need to do is in your organization table file directory structure, all you need to do is you have a table like this. You will say that okay, file a.txt is my name and my attributes, and this would be my start block and the number of blocks. Okay, so I have many of these in a directory entry. So I have many of these in a directory entry. So no problem. I can do that. But the problem the problem with this approach was external fragmentation, and when we try to append a file, it is costly. Okay, external fragmentation. And okay, this bad network quality is even worse today. Okay, external fragmentation and the appending is costly. That was the problem. But even with the problems, because contiguous layout used with the CD-ROMs, that's what we said last time, and then we, oh man. And then we said that let's try to deal with this problem of contiguous layout, and we came up with this idea of linked file allocation. We said that this would be our structure. Okay, this would be our structure. And for each file, all I need to do is provide blocks, and each block is linking each other. So I have a linked list implementation. A linked list implementation, as you know, from data structures course, okay, from the data structures course. If you know about the linked list, you're fine. If you don't know, just read them. We know that they are very good for appending, like inserting a new block in between. For example, if I like to insert a new block here, all I need to do is just break this link and make this link and make this link. Okay, so appending, modifying files is fine. And you don't have any external fragmentation issues anymore. Why? Because I don't have to store anything contiguously. But the problem was poor access speed, especially the random access is so poor. Why? Because I need to read each block one by one to access the, let's say, Kate. Waiting for the, okay, to access the Kate block. So that will take lots of time because accessing the disk is not an easy thing. It takes lots of time. That's why we didn't like it much. And we said that sequential access is not cheap either. Why? Because this is so bad today. Okay. So this would be our directory structure, file name, and the starting block number. And I do this. And I said that sequential access is not a good thing for this kind of approach because, as I said before, last time I think I drew this. These are our tracks. I have my tracks, and let's say these are my blocks. One block might be there, the other could be there. Let me use a different color for the blocks. Okay, one block, another block, another block, and another block, and they are linking each other. So they are on different tracks, on different parts of the track. So to read a file, you need to do lots of head movement of your desk, which is not a good thing. It is slow. So what was our solution? Our solution was to come up with this table in memory. Okay, so I think last time we stopped here. Our solution was here. It was table in the memory. So with the table in the memory, linked list table is the memory. It's a regular linked list now. Okay, let's say in my disk partition. Okay, okay, in my disk partition, let's say these are my blocks. Okay, these are my blocks, and let's say I have 16 blocks. So this is a very small disk. All I have is 16 blocks. So I make a array of blocks on my in my memory, is in my main memory, and I say that if I have two files in my directory, then let's say this is my directory listing, uh, file A and file B. For file A, the starting block number is 7. For file B, the starting address is 3. So what do? I just read this. Okay, this is my directory. To find the file A is here, and I go to the array of my blocks in my memory, and I follow the links there. So following the links is not did not change. I am following the links, but while I am following the links here, okay, I am not reading the disk blocks. Okay, so I am doing a very fast thing compared to this access. Still it's a linked list, but my linked list is in the memory, not it is not in the disk. So if I okay, 7, it links to 7. Okay, so this would be the linked list structure, and each one is ending with a -1. So all I am saying is that we didn't change much, but all we did was we took the linked list out of the disk, we took them in the memory. So what would be the primary disadvantage of this method? So somebody tell me, that's the question here. What would be the disadvantage of this method? Anybody? Ali Haydar says that it uses too much space. What space, Ali Haydar? Disk space or you mean memory space, right? Yeah, I think he means memory space. I need to keep this table in my memory, right? And since this is a toy example, I have only 16 blocks. That's fine, but let's say I have uh, I have, let's say, 1 terabyte of disk space. That means I have 2 to the power of uh, 30, right? Bytes on my desk. No, is it 30 or 40? Okay. Kilo, mega, giga, and tera. Yeah, 40. So I have 2 to the 40 bytes on my desk. Let's say each of my block is 1 kilobytes. Then in that case, I need 2 to the 30. Okay? 2 to the wait. I have 2 to the 30 size page, okay? 2 to the 30 size array in my memory. So that's billions of words, right? Billions of integers. That's gigabytes of data. I cannot keep all that gigabytes of data if my main memory is just 8 gigabytes, right? So that's too expensive. But some file system are using this approach, especially the popular file access table, FAT16 and FAT32. FAT is using FAT uses this approach. I have another idea. Let me connect to this meeting with my cell phone. Okay, I am using my cell phone right now. Maybe if I send my voice from my cell phone, I should be fine. But for that, I need to. Okay. I am not hearing myself. And are you hearing me right now? Are you hearing me right now? I cannot hear you. Just type. Okay. Is this better? Is this causing any interruptions? This is weird, but let me do this actually. Let me turn on. Okay, somebody say something. Somebody say something. Are you talking? Oh, okay, I hear you now. Okay, good. I hear you from my cell phone, and you're gonna get my voice from my cell phone. I will read your messages from there, and I think okay. Let's do it this way. So I know my internet connection is very good. I know this. Okay. I think that the Teams is compressing it too much, and it is using some kind of a upstream compression protocol, and it is not sending the bytes one by one. It's just sending them by buffering it, sending it later, and that causes interruptions. So if I load my network artificially like this, then maybe I am solving something. I don't know. Let's see. Okay, so we will do it this way. FAT16 and FAT32 is like this. So, but with FAT16, there is a limit. I mean, you cannot have a file access table. This is called a file access table of size, let's say 1 gigabyte, because it says that all I can access is 16-bit block numbers. Okay, all I have is 16-bit block numbers. That means that you may have at most 2 to the power 16 blocks. Okay, 2 to the power 16 blocks. It makes I think it is 256. Is that true? No, 128, right? How many kiloverse is this? It is 5. Okay, it is like I think 128, right? Or 64. 64 kilo blocks. Okay, and if each block is like let's say 4K, then 4K is then that makes 2 to the 28. So the total disk size could be at most 256 megabytes, right? So that's small. 256 megabytes is small, but with FAT16 all you can do is otherwise your FAT becomes too big. Okay, so that would be the problem. Advantages of linked list. no disk access file and following the links. Disadvantages, it still needs to traverse, but you don't use your desk blocks to make this traverse, and it uses lots of memory. Okay, so if you have a 200 gigabyte disk and each one is a 1 kilobyte block, then that means you need 2 to the 20, so 200 megabytes of memory space. That's not affordable. Okay, yeah, okay, it looks like I am doing good. Yeah, okay. It didn't cause any interruptions, right? Good. Is nobody saying anything? Say something. Are you guys hearing me? Okay, good. Okay. So Mustafa says that it is not better. Mustafa, you always have problems. I don't know what to do with you. I will give you a separate lecture for you on the phone. Okay, let's deal with. Okay, let's start from the beginning. We didn't like the contiguous allocation fragmentation issues. To solve the fragmentation, linked file allocation, then working on the links is expensive on the disk. Then we brought everything, all the linked list to the memory. Now it takes lots of memory. So what am I gonna do? The solution comes from the Unix. They call this index allocation. Inodes. The idea is this. Why are we keeping all the block table in my memory? Okay, only keep the linked lists of the open files in the memory. Okay, don't keep the whole disk's linked list in my main memory. Okay, so that's the idea. So that's the idea. I am trying to see if I am recording everything and my voice is fine. And oh, okay, so my captions are working too, even though I am sending my voice to that through the cell phone. Okay, good. Go back to this. So the idea is let's keep only the indexes in the of the open files in the memory. Just keep all the attributes and addresses of each block belonging to file in structure and keep in memory only when the file is open. So advantages, of course, in terms of memory space, okay, main memory space efficiency. There is no external fragmentation, of course, like all the linked list approaches. But this time I have this overhead of index blocks. So let me show you an example, okay? This is an example of an index block. In the index block or inode, okay, index node or index block, I have my file attributes, and then after that, inside that one, I have the addresses of my block 0, block 1, block 2, etc. for my files, okay? And if this space is not enough for a single block, let's say I have 1 kilobyte of inode. If this space is not enough to keep all of my pointers, then the last entry in my inode is another pointer to another block. Okay, so that's the idea. So in this case, how is my directory structured? Let's look at that one. I would say this is file A, then This one gives me inode number. Okay, so this one just is a pointer to an inode, index node, and that index node has the file attributes, file name, creation time, last modification, etc. And I have the addresses of all of my block inside this block. So whenever I open a new file, okay, I load this inode from the disk to my memory. I keep only this one. So I don't have to keep all the linked list of all the files in my memory all the time. So this is a better idea, but the problem is with the inodes. I need to keep separate inodes for the files. Remember the general structure of the disk. I showed you this one, right? So with this disk partition, okay, it's a Unix partition. I have my boot block to boot my computer if this is the active partition. Super block contains the file system related stuff, okay. And free space management, another specialized place. And I have these inodes. There is a special place on my disk, okay, that keeps the inodes. And there are many inodes available. And I use these inodes to keep my indexes for each file. So there are limited number of inodes on my desk, and I need to use these inodes so that I can keep my indexes on the disk. So if you lose by accident, if you lose some of your inodes, then your files will be corrupted very badly. So inodes are so important. Inodes are important. If you lose your inodes, it's losing. That means that you are losing very big chunks of your file information. Okay, so that's the inode idea. As we call it this index allocation. Is this like lazy loading? Lazy loading? You mean that compared to the in-memory indexing, you don't load the whole thing? Well, I mean, I think you are, Ahmed Yasir, you are trying to compare this with the previous approach. With the previous approach, there is no loading. This table is always in your memory, okay? The loading time is when you mount your file system, okay? When you introduce your file system to the operating system, you load it. You don't load it part by part, okay? But this one loads the inode whenever the file is open for reading or writing. If you like to call this lazy loading, then you can call it that way. Yusuf says that what if we run out of inodes? That's a bad thing. Yeah, I mean, you shouldn't run out of inodes. But the thing is that, I mean, how would you run out of the inodes? Each inode contains these pointers, right? Each pointer has to point to a block. If I have, let's say my disk has 2 to the 30 blocks available, okay, and each block is, let's say, 1 kilobyte, so my disk is 2 to the 40 disk, so it's a 1 terabyte disk, okay. If I have 2 to the 30 blocks, and let's say for each block, for each inode, each one is a 1 kilobyte. Let's say I can fit if I have block size 2 to the 10, okay, and for each block I need to keep this address, and I have 2 to the 40, 2 to the 30 blocks. That means that I need to keep 30 bits for each one. 30 bits means that 30 bits means that I need to keep 4 bytes, right? I need to keep 4 bytes, and 4 bytes is 1 kilobyte. 4 bytes, I am going to divide it, so 256. For each block inode, I can fit this many blocks. Okay, 256. Okay, 256. I know how many blocks I need. If I allocate this many blocks for my desk, then I should be fine. There is no way I will be out of inodes. So there is a calculation that you can do. So you don't select your inode space size randomly. There is a calculation. Why do they limit the inodes? Well, they don't limit the inodes. I mean, all I'm saying is that there is no reason to keep lots of inodes. Kamil, you are saying that let's keep the inodes with rest of the files. I mean, why inodes are special nodes? They are special because you need to load them very fast. Okay, you keep your so to answer your Kamil's question, inodes are special blocks, and I keep them in a special place on my desk so that I can read them very fast in a sequential way. So usually, let's say this is my desk. These are my tracks. Okay, I keep my inodes on a single track like that. And if I need to load some inodes, I load them in a very fast way. I don't like to distribute my inodes all around the desk. That would make it slow to read them. So back to Ahmet Yasir's question. So yeah, in this approach, we only load the metadata, not the contents, unless it is necessary. Well, yeah, but that's a good way of looking at it. Yeah, you can say that. You can say that. So you load the metadata and the block information of your file to your memory at the beginning. And if you are doing sequential access, there is no escaping from that. You load your blocks one by one. But if you are doing a random access, you know which block to load without loading any other blocks. Okay, and if you are appending and if you are inserting blocks, then you should be fine. Okay, so those are good questions. But those are good questions, but I know this is a very important concept actually. So Unix people have been using this for a very long time. And it solves external fragmentation problem. It solves too big file access table problem. And of course the disadvantage of the overhead of inodes and being very careful about your inodes. Okay, so this was how you store your files, but before that, okay, we have the directories, right? Without the directories, there is no way I can access the files. And remember, this is what I said about the directory structure in the inodes. In the directory structure, you have your file names, and with each file name, you have the inode number. Okay, that was how I told you you would implement your directory. That was the inode directories, and this was the FAT directories. With the FAT directories, what you do is, okay, with the FAT directories, what you do is you keep all of your files and attributes and everything. By the way, I mean you need to keep your you need to keep your attributes in your directory listing with the linked list approach. With the inode approach, you keep your attributes in your inodes. Okay, so this is one important difference, because your directory listing only here says that, okay, start from the seventh entry. Seventh entry is here. No, where is file? Okay, here. Oh, this is wrong. This is wrong. This is okay. File A starts at 4 and file B starts at 6, right? So this one says that file A starts at 4, block number. That's it. Okay. Where is the attributes? Where are the metadata? So you need to keep them in this table. With the inode approach, okay, with the inode approach, you don't keep the attributes in your directory. You keep your attributes in the inodes. Okay, so let's look at how we organize these directories. Okay, of course, it depends on the system. Okay, the directory entry provides the information needed to find the disk blocks. That's okay. That's one of the important thing. But the other important thing is that the attributes too. And depending on the system, this information may be the disk address of the entire file, like the contiguous allocation, or the number of the first block. Okay, FAT approach, or the linked list approach, or the number of the inode. Okay. In all cases, the main function of the directory system is to map the file ASCII name to information that need to locate the file. So directory kind of does this. You give the file name, including the full path. Okay. It gives you the block number of the starting address, or the inode of the starting address, or the address of the first byte of your file. So this is what the directories do. And for some directories are organized this way. Okay, you need the directory name, okay, the name of the file inside your directory, and the attributes, and the starting address. Or for the inodes, or the other block-based directories, the name and the attributes, and inside the attributes you have the starting block number. Okay, so starting block number could come from the linked lists here. Okay, from the list here, but these are the block numbers: block number 1, block number 1, etc. This one, block number, comes from the other nodes. Okay, so B is like inodes, A is like for contiguous allocation. Okay, so these are important because when we look at the hard linking and the symbolic linking, this will make some difference. Okay, so if you have, okay, remember the picture that I tried to okay, let me copy this. Duplicate and copy. If I can. No, I couldn't do it. I kept drawing pictures like this. I kept drawing pictures like this. I said that, okay, there is this file name and starting address and etc. But the thing is that I assume that file name 1, file name 2, file name 3, and these are the starting addresses. So let's say this is a contiguous allocation file system. I assume that the file names are fixed. Okay, that means that I have 8 characters or 10 characters at most. So I assume that this is, let's say, 80 bytes, again 80 bytes and 80 bytes and 80 bytes. So this is what I assumed. What if the file name sizes are not fixed? What if the file name could be as large as possible? Okay. If the file names is fixed, then this could be the structure. Okay. This is for file name file 1. This is for file 2 and file 3 and etc. Okay. So this would be my structure. But if the file name size is not fixed, it could be as large as 1000 bytes. Okay. Then what am I gonna do? This structure doesn't work. So they came up with this idea. They keep kind of a heap space in another space, in another part of the disk, in the same node maybe. So all the fixed stuff, pointer to the file1 attributes are there. This is fixed. But I have a pointer to the heap to tell me the file name. Okay. And so this is how you address. This is one of the ways you address the unlimited file name length approach. Yusuf says that Unix forbids the slash character for files. Is this related with this architecture? No, because slash is used for separating the directories, right? When you get the full path name, you would say mount a user. So slash has a meaning. Slash is used for separating the parent directories from the child directories. So this has nothing to do with slash. And I don't understand your question. Why did you ask this question at this point? Okay, just if you like to ask more questions, you may ask it. So when you implement the files, as I said before, I mean, each entry is a fixed entry. Each entry is a fixed entry. And if you have variable length file names, then you could keep pointers to some heap space on your disk. Okay, good. So another issue with the directories is you may have to have very long directories. Okay, you may have to have very long directories. Let's say the number of elements in this directory is, let's say, 10,000. Okay, so and I keep this information in the disk. When I load this directory to my memory, if somebody says that, is there a file named file1.txt, then I need to make a linear search on it, right? So making a linear search on this kind of size sometimes is expensive if I do this a lot. Okay, if the directory contains many files, making a search on it, okay, can be slow because it's a ON operation. Okay, so in this case, maybe we can use a hash table to speed up my searching of the files inside my directories. Okay, so that could be one thing. So this hash table is a table on the disk. When you ask that directory, do you have this file? Okay, and how does the hashing works? Let's say this is my hashing function. I take f1.txt, and this one gives me This one gives me a array address. Okay, I directly go to that array address and I try to see if the file is the same if I have a hit. Okay, so that would be the second that would be the first way of speeding up the things. The other one is, instead of reading the same data from disk over and over and again for large directories, let's keep a cache of directories. I mean, there are some popular files. I mean, people try to access those files all over again. So let's keep a cache. Okay, don't try to read everything from the disk. That's the second approach of speeding things up. Okay, there are many other issues with the directories and everything, but the book just lists only a few important issues. Okay, good. Any questions? So we looked at the files, then we looked at the directories. Let's look at this sharing file stuff, and I keep delaying talking about these soft links and soft links and hard links, and I will talk about them here. Okay, hard link versus symbolic link. Okay, and in fact, let's talk about it here. So, assume that I have a directory structure like this. I have three users, user A, user B, and user C. And user A has a file, these are directories, the square ones are the directories, circles are the files. User A, this is so confusing, let me make this a little bit better. A1 is the file name, okay, B1, B2, C1, C2, C3, these are the directory names. Oh, okay, there is this B3 here. Okay, so there is no confusion now. Okay, each user has, oh, no, this is B. Okay, good. So each user has his own directory, and under the directories, I have the files and other directories. Let's say I like to keep this file shared between these two users, B and C. How am I gonna do this? Yesterday we looked at this. We said that we can do linking, and I showed you how to do this linking with Unix command link. Okay, so there are some issues with this, but before the issues, let's look at the difference between the hard linking and the symbolic linking. But before that, I think I will take a break. Okay, let me take a break. After the break, we will continue. Okay, so I will take a break. 11:21 now. Let's come back here. 11:31. Okay, break. No, I did not. Okay. Now this is working fine. Um, let's go back to our directory structure again. I said that K1 is a small file now. It contains this information. So for K1, if it's an inode representation, I need to have another inode. So it's a file. So whenever try to I access this K through K1, I need to open another file. That's an overhead, right? So hard linking is more efficient if it works. Hard linking is more efficient if it works. Okay, good. So that's the difference between hard linking and soft linking. The book has some issues about the shared files. Okay, some problems with the shared files. If you keep your block list in your directories, then hard linking is a problem. Why? Because if you keep your blocks in your directories, then if you update something, the other file will not see it. That's a problem. But inode solution solves this problem. But with this now, there is a ownership problem. What's an ownership problem? It's this. Let's say I have CS directory. Okay. Inside this directory, I am pointing to this inode, and inode says that for this inode, the owner is C, and there is only one file is pointing to it. So I am keeping the count of references to the inode. Okay, so there is only one count. If B is pointing to that inode, now I have the count of 2. Now I have the count of 2, right? So 2 directories are pointing to the same inode. This is my inode. So if I keep the number of counts, I would know when to remove the file from the system. If the number of counts is more than 1, don't remove it. If the number of counts is 0, then remove it. Let's say I have removed the file from C's directory. Now I have this one. So far so good, but the problem is B is now pointing to an inode which is owned by C. And if the system administrator removes C from the system, whole system, then this would be a very weird case, because there is a file owned by somebody that doesn't belong to the system, and it is used by B. Okay, and it is used by B. So the hard linking has some other problems too. Okay, so Edis has a solution. Edis says that, can we switch the owner of the file if the original owner deletes this file? No, you cannot. You should not. In fact, you should not. I mean, if C says that I am deleting this file, the owner is still C. Okay, if it's a let's say my file is read, write, and read, and this file. Okay, so the original owner can read and write. The groups and the others can only read. Okay, in this case, I don't want to switch the owner from B to C, because C doesn't want others to write to his file. Okay, Edis, do you understand this? I cannot do that by default. He says that when we do this, let's change the owner from C to B. No, it may not be possible, or it may not be desirable for some cases. Okay, so sharing files is nice, but it has some problems. Good. Now we understand the difference between symbolic link and a hard link. If C wants to delete, why doesn't it fully delete it? If C says that if C says that I want this file to be deleted and nobody else should see it, there are ways of doing it, but in this case it looks like C say that I don't want this file to take space in my directory, but if somebody else is using it, then they can use it. What's wrong with this one? I own the file, but I don't want to keep a copy of it. I don't want to keep a copy of it in my directory. Okay? If somebody wants to use it, then they can use it. And if C doesn't want anybody else to see it, that file to be linked, then in that case, C wouldn't set the permissions like this. Okay? Good. So for some reason you guys like this shading and hard linking and soft linking. Okay, good. Okay, let me move on then. If there are no questions, let me move on to log file systems. The thing is this: our computers are getting faster and faster and faster. Okay, CPUs are getting faster, memories are getting larger, but disks, especially the mechanic disks, they are not getting that fast. Okay, they are still slow. Of course, I mean it used to be maybe a seek time would be maybe 100 milliseconds from 30 years ago. Nowadays it is like a few milliseconds, maybe 5 milliseconds nowadays. So that means that 20 times more speed for the disk access. But our CPUs are now maybe 10,000 times faster. So CPUs are getting faster much more than the disks. So and we are getting much larger memories. So the idea is, when we read data from the disk, it is expensive. Let's read lots of data because of the principle of locality. Let's save lots of data and keep them in a cache. Okay, so we kept using these caches. So it looks like this is so efficient. Most of the time, I don't need to go to disk to read some data. I read most of my data from the disk cache. Okay, disk cache. And disk cache, sometimes they have disk caches. They sometimes they have like some disk caches. They have 1 gigabyte of disk cache space, 8 gigabytes of disk cache space. Sometimes you see that. So they are very, very large. Sometimes they are very, very, very large. Some expensive disks. So most of the time you do your reading from the disk. But when it comes to writing, I cannot do this because I don't know. I mean, when you are reading, you read more. Okay. If the user says that read block number 100, okay, I read all the blocks from 80 to 120. This is called read ahead. Okay, this is called read ahead. Principle of locality. I can do this with the reads, but when it comes to writes, there is no such thing as read ahead write, because to be able to write something, I need to know what to write, right? So I cannot do this optimization when it comes to writes. So when you are writing something, you need to go to the disk and write it. And most of the time, these writes are so slow. You need to get the inode. You need to update your inode, and you need to put all the data in your corresponding blocks, and you need to update all of them. Okay, so it is not just single block updating. Even if it is that, it would be expensive. So the idea is, with the log file systems, keep everything buffered in the memory. All the writes are initially buffered in the memory. Okay, keep them buffered in the memory. When that buffer is full, periodically, okay, all the buffered writes will be written to the disk as a single segment. You are writing everything to the disk at a single segment, very closely related tracks. So you are not writing them to the original locations, but at a different location. So this causes some fragmentation issues, yes, but for that one, they run different threads that kind of make a cleaning job of this segment when the CPU and disk is free. Okay, so this log file systems has this property of, okay, lead rest of data, keep them in the cache. Also, your writes are not direct writes, write them to the buffer. Okay, if the buffer is full, write the whole buffer to the disk at the same time in a single write. So what am I gonna do with these original inodes and the blocks and etc.? You change their spaces. Okay, you need to handle it. So it's kind of messy to deal with this problem. Okay, you are not writing the original inodes to the original places, original blocks to the original places. But if you are careful and if you do the bookkeeping right, this could be very efficient. This is called log file systems. Okay, any questions about log file systems? And the book has a very good discussions about it. You read it on the book. Another technique used with the file system is the journaling file systems. Journaling file systems. Okay, Ahmed. Yeah, Ahmed has a very good point. I mean, if you keep all of your data in a buffer, let's say you kept 1 gigabyte of unwritten data in your buffer, and the system crashes, what happens? Then you are in a messy, very, very messy situation. You are in a very, very messy situation in that case. Okay, so you will be in trouble. You will be in trouble. That's why. I mean, but this is a known fact of life, especially with the Unix systems. If you don't shut down your computer properly, your system crashes, right? It's because of this, because Unix uses lots of temporary buffers that are kept in the memory, and from time to time they are flushed to the disk. If you don't properly shut down your system, that is, if you crash your computer, if the power goes off, then you will be in trouble. Maybe this journaling file system is a solution for that one. This one says that before you do anything on your desk, you keep a journal of what the file system is going to do before it does it. Okay? You say that, for example, this is a good example actually. Okay? To remove a file in Unix, this is what you do. This is your structure in Unix, right? This is your directory. These are your directories. Let's say this is your file, and this is your block number, inode block. So this is your inode block, and this one points to lots of other blocks. This is how you represent your files in Unix, right? So whenever you like to remove a file from directory, this is what you do. First, you get rid of the file from the directory. Then you need to release this is inode, and these are my blocks, 5 blocks. And you need to get rid of your inode. Then after that, you need to get rid of your blocks. Okay? So Ahmet Yasir's question, what happens if the system crashes between these steps? What happens if my system crashes here? What happens if my system crashes there, right? So if the system crashes between 1 and 2, if the system crashes between 1 and 2, That means that I will not see that file in my directory listing, but its inode will be garbage inode. Nobody is going to be using it. So I wasted that inode. Also, all the blocks that the file occupies will be junk blocks. Nobody can use them anymore. Okay? So that's a bad thing. That's a bad thing. If the crash happens, if the crash happens between 2 and 3, if the crash happens between 2 and 3, inode will be free to the inode pool, but all the blocks will be unused blocks. So these are, in this case, I am maybe lucky because in this case, if I do this in this order, in this case, I am not causing any file system crashes. This causes only file system inefficiency. But for some cases, there would be situations where two inodes are pointing to the same block, okay? Or a file name pointing to an invalid inode. That may be a problem. So the journaling file system says that before you do anything, before you do any of this stuff, just keep a file of what you are going to do first. Keep a journal of what you are going to do first. Write to some position, say that you are going to remove this file and you are going to release its inode and you are going to return all the blocks, okay? So the system knows what you're going to do and you do it one by one. If the system crashes, and when you boot up your computer again, the system will see that you executed only one or two of these steps, and the system knows what to do next. Either it will undo the first two steps, or it will do the third step for you. Okay, that's called the journaling file system. Keep a journal of what the file system is going to do before it does it. If the system crashes before it can do all the planned work, upon rebooting, the system can look in the log to see what was going on at the time of the crash and finish the job. Either it will finish the job or it will undo whatever you are trying to do. Okay, these are called journaling file systems, and NTFS is such a system. Linux ext3, okay, resilient file system are some journaling file systems. It is very difficult to crash NTFS while it is writing something to the disk, while you are removing a file, updating a file, copying a file. You crash your system, and when you turn back, you will see that your files are fine. Okay, so Ahmed, is this kind of an answer to your question? So do both log file systems and journaling file systems at the same time. Well, I mean, I am just talking about them using a single slide. These are very complicated things. It is not easy to write file system that can do the journaling. Okay. In fact, this Linux ext3, it took more than 10 years to develop because you need to keep compatibility with the ext2, right? What if it crashes when journaling? When in that case, Selman, when you are doing the journaling, if the thing crashes, that means that you didn't do anything bad on your disk, right? So you didn't do anything on your disk yet. Your journaling is bad. When you do the journaling, I am not saying that your processes will continue as usual, but I am saying that your disk will be kept in a stable state. Of course, when you crashing is a bad thing. Here we are trying to keep our system stable. If your system crashes when you do the journaling, when you are saying that I am going to do this and this and that, okay? If you do that, that means that while you are journaling, you didn't do anything on your disk yet. You are writing a journal and it is not done. When the system wakes up, it will see that there is a unfinished journal writing and it will ignore that journal. In that case, of course, your process will be a bad process. It is not done, but your disk will not be in a bad case situation. Okay, any other questions? Okay, if there are no questions, I will continue. Virtual file systems are used by Unix and other operating systems a lot. Windows has kind of a solution for, let's say, on my system, on my computer, okay, what kind of secondary storage do I have? I have my SSD, I have my CD-ROM, and I have my USB sticks, right? So each one is using a different file system. Each one is a different file system, and I need to take care of this technology differences between the file systems. Windows says that, okay, for this SSD I will assign the letter C, for CD-ROM it will be D, for USB it will be E. So Windows says that, okay, for each file system there would be a different drive letter, and it kind of says that if you like to access a file, then go to this D, then otherwise E. But Unix doesn't say that. Unix says that everything is under this root directory. Under the root directory, you have your user, you have your bin directory, you have your mount directory. Maybe under your mount directory, you may mount your C drive there. Maybe you may mount your D drive there, but everything is under the same root. Okay. They make a very serious attempt to integrate multiple file systems into a single structure. And then they say that there should be a way of doing this. I mean, the user should not be able to know, users should not know what kind of file system they are using. Okay? And this is the solution. I have this virtual file system. My user processes, they always think that they are using their regular POSIX interfaces. What was the POSIX interface for the file? I open my file, I create my file, okay, read and write, okay. These are my POSIX interfaces, right? How I open a file, how I create a file, how I write a file might be very different depending on the file system. Let's say this is the file system for CD-ROM. This is the file system for my SSD, okay, drive, and this is the file system for my, let's say, hard drive. For each one, creating a new file is different. Okay, creating a new file is different. They are using a different file systems. So I need to take care of this situation by introducing this virtual file system. Virtual file system says that if you are going to be a file system on my machine, then you need to implement this virtual file system interface that I am marking with double frames now. Virtual file system interface. So the virtual file system interface, it has two interfaces. One is POSIX interface, the other one is the up interface is POSIX, down interface is the virtual file system interface. So how does this virtual file system interface work? It works this way. Okay, I have my process table. Inside my process table for each file, if you remember, I have my file descriptors. In my file descriptors, whenever I open a file, okay, I have a file descriptor, and in that file descriptor, I have a pointer to my inodes to get the attributes and everything. In this case, you have a pointer to vnodes. That's the virtual file system node, okay, and those vnodes are different for each file system. Why are they different? Because they keep a pointer to a function table. This is like virtual functions of C++, polymorphism, okay? So each file system says that you're gonna do opening, reading, and writing using these functions. Okay, so each file system provides functions for opening, reading, writing, appending functions when they are mounted to the system. And the virtual file system just says that, okay, I'm going to call the open function or read function or write function of this file system to perform this task. Sometimes some of the operations are not possible. For example, for the CD-ROM file system, there is no create function available, right? So when you call that create function, it returns you an error code -1. So the virtual file system says that there is a problem creating this file. Okay? So this is how the whole picture virtual file systems work, and this is practically used by the Unix operating system. It is practically used by the Unix operating system. Of course, similar techniques are used by the Windows and operating systems, but I think, but I think this is a nice solution to be present in a single page. Ahmed has a question. Does this method have a significant performance overhead? Well, I mean, the performance overhead is the same as polymorphism, right? With the polymorphic calls, you had this problem of going your virtual function table and finding the function and calling it. The overhead is the same as that, but in this case, the situation is better. Why? Because at the end of these function calls, there is a disk read write, and disk read write is much slower, thousands of millions of times slower, okay, than following these links. Yeah, there is an overhead, of course, but compared to disk read write, secondary storage access, this is ignorable. This is very, very small. When you start dealing with the disks, remember the table that I showed you before? When you go to the disk, the things becomes millions of times slower. They are very, very slow. Okay, good. Any other questions? Okay, if there are no questions, then I will talk about file system optimization. Up to now we talked about optimization. Okay. Up to now we talked about what is what. Okay. I introduced you inodes and fat tables and log file system, journaling file system, etc. I just introduced you new ideas. But we did not talk about optimization, how the things could be faster. So the first thing that we are going to discuss is the block size. Okay. How should I adjust my block size so that my performance is optimal? Okay. Two general strategies are possible for storing an array of a data of n byte file. Okay. I could consecutively put n bytes directly to the disk, okay, or I can split the file into a number of not necessarily contiguous blocks. So contiguous representation has advantages, but it has some fragmentation issues and the appending and that kind of stuff. That's why we don't keep all of our n bytes contiguously. We separate them into blocks. Okay, we separate them into blocks, and with the blocks I can separate my files and I will put them in different places. Actually, we had the same discussion when we talked about memory management. Let's say we said that should we have pure segmentation or segmentation with paging? Pure segmentation was good because each segment is a linear segment from 0 to some big address, but it has some fragmentation issue, compaction issues, and etc. If I use a segmentation with paging, it becomes much better. I don't have fragmentation issues, I don't have allocation issues, and etc. So we are going to do the same thing. We are going to say that our file is divided into blocks, and I need to determine the block size. Okay, how big my blocks should be. If the block is too large, then even for the smallest file, I will, I will, I will need to use that many bytes for that block and for that file, and I will waste space. That's called the internal fragmentation. If the block is too small, then to reach my file, remember the index access. For each block, I need to keep these indexes and I need to follow those indexes. It's wasting time and space. So I need to find a trade-off. I need to find a sweet spot between small blocks or the large blocks. That's the idea. But it looks like I am out of time today. So I think I will continue on Monday. Okay, that's it for today, if there are no questions. Are there any questions? Okay, I'm happy today that I found this solution to this staggering and the interruptions and the synchronization problem at the same time. Thank you, Mustafa. You too. Ahmet Nasir, we are working on it.
Ahmed, I will declare the results in the week.
Okay, so you got the answer. So, Fırat senle bir konuşalım. İlhan sen de çıkma ya. Fırat'la bir konuşalım beraber. Herkes,
Tamam hocam.
herkes çıksın arkadaşlar. Fırat'la konuşacağız.